Our next speaker, it gives me an incredible pleasure. My friend from 45 years back. We grew up together, incredibly talented, brilliant individual, Dr. Surya Iyer. Surya is the CEO of Polar Semiconductors. He's going to tell us the challenges they face in the real world. I mean, we sit here in our ivory towers and think that we got things figured out, but the real world tends to be quite a bit different, I figure. So, Surya, we're looking forward to your insight.
Him and another neighbor friend of ours used to. I have some memories. We did, yes. But it was good old days. So thank you. While we're getting set up here, I just want to say, really a pleasure to be at this forum and honored to be invited to speak. I'm going to try and bring. By the way, can you, the people in the back, hear me reasonably well? Okay, good.
So which one's yours?
Mine's this one, last one here. Yeah. And so I want to bring a perspective from the industry point of view. I'm going to talk, as the slide deck is being set up here, I'm going to talk first, introduce the company that I work for. Some of you may have heard about it. We're kind of the claim to fame is that we were the first CHIPS awardee in the United States. So as Polar Semiconductor was the first company to get CHIPS award under the Biden administration CHIPS and Science Act. So I'll introduce Polar very quickly. And then talk about our evolution of collecting data, using data, and controlling the process in the manufacturing facility. And then go a little bit deeper and talk about things that I think would be useful in making Polar more competitive in the world as a manufacturing facility in the United States. Just to kind of bring the economics perspective, manufacturing of semiconductors is dominated by Taiwan mostly, and to some extent China is now catching up. But the whole point of the CHIPS and Science Act and other initiatives, both in the previous administration and this administration, is to try and bring that manufacturing capability and capacity back to the United States. How successful that's going to be depends on a lot of things. And one of the most important things is that how can we keep the technological edge while keeping costs down and efficiencies high. So that's kind of part of the discussion that I'm going to get into a little bit more today. And then introduction to Polar in one slide. Polar is a company that's been here for a long time, actually. We started as Control Data. So one of the original computer makers in the US was Control Data, and it has transitioned over different ownership. Most recently in September of 2024, just as we got the CHIPS Act money, we also got private equity, so we became not only a US located company, we became a US owned company. And that has implications in terms of national security and other things that will also be relevant to this discussion. We are a power semiconductor company. The previous presenter talked about a lot of power being used in AI computation, servers, and other things. Our specialty is power management chips. So we make power management chips that go mostly into automotive, but also to a lot of different applications in now growing into the AI ML space than ever before. Any of you interested, in visiting Polar, I'd be more than happy to host you. If you're a student, if you're looking for positions and jobs, I'd be more than happy to talk to you. We are growing, we're expanding, and we need the smartest people that we can get. And that's another piece of that competitive edge to our competition across the world. So we're about a 600 people company. I don't want to spend too much time here. This is not an advertisement for Polar. Let's move to the next. This is kind of our evolution, where we have been and where we want to go. And almost every semiconductor factory, or fab, as we call it, is a highly automated factory. Everything, as much as possible, is automated. That's because it needs to run 24/7, 365. We don't stop for Christmas. We don't stop for Thanksgiving, Ramadan, Diwali, or any of that stuff. It keeps going all the time. And so you need to have a lot of automation. You need to have a lot of efficiency. The amount of investment that you put into a semiconductor fab is incredible amount of numbers. For example, the expansion Polar is doing is $500 million. The kind of expansion that Analog Devices or Intel or TSMC or Samsung are doing are another 1 or 2 orders of magnitude bigger. 20 billion, 200 billion approximately from Micron. So these are large numbers. You have to make sure that the factory is running all the time, high utilization, so you get the economics to work for you. So some of the things we have implemented over the past, maybe let's say 10 years or so, are things like the FabGuard system, which is a fault detection system. It collects data from machines and tells us if something's going wrong ahead of time, so we can shut it down before we scrap thousands of wafers and destroy the product. We're using a lot more robotics. If you walk into the fab, you'll see R2-D2 and Rosie and all these robots walking around the fab. And that is huge in terms of efficiency and speed. In the past, we used to have operators move everything through carts. Literally, operators would be walking about 12 to 13 miles a day in a shift. Incredible amount of strain on knees and other things that are now avoided by the use of robotics. We've also introduced something called, about a few years ago, we introduced intelligent scheduling system. So you can imagine about 500 pieces of semiconductor equipment with about 60 to 80,000 wafers, 8-inch wafers in the line, have to be optimized so they can find their way from step number 1 to step number 450 or so with absolute efficiency, fastest way out of the fab. That is an incredibly complicated optimization problem. Again, ripe for things of the nature that you all are experts in, right? That's one of the key applications that would be very useful. By the way, the TSMCs and the Samsungs of the world have 400, 500 AI engineers, AI ML engineers working for them. And I'll tell you how many of them are working at Polar in just a second. The other things we're doing, are really starting to get into the AI ML world, right? And I think that is the differentiation that we need to be successful and to be able to compete. Because at the end of the day, if we can find and squeeze out those efficiencies in a factory that is transforming, has a much better chance of success than a factory in Taiwan, for example, that's already established and just runs. So you have that chance of catching up and beating them. Some of the AI ML efforts, again, I revealed the number of engineers that we have at AI, a total of 1. So 2 of them working 50% of their time. They're also, device engineers, right? So they do data analytics on the side. We started in 2019 with an engineer. We sent this engineer to Georgia Tech to get a certificate or a degree in AI ML. And this person came back and really has transformed the amount of activity in this field that we're doing now. We just hired, I think just about a few weeks ago, our second AI ML person, University of Minnesota master's graduate, undergraduate and master's student. So excited to have her in the team as well. So kind of the things that we're doing are automating tasks. We're doing some computer vision. I think that was original success, was just image type of analytics, just comparing images, finding defects. That was one of the initial successes with the effort. We're also now using natural language processing and other things. I have to, I mean, if you haven't judged already, even though I am technical, I'm an engineer by background, I really have no idea what all of you were talking about in the last session. So, but I did take a class at Wharton on AI for managers. So I know how we can use it, how we can make money out of it. So here's an example of what we do. This is something, you know, we are a somewhat of a manual factory. We still have operators in the fab and a lot of equipment. Some of the equipment is older compared to the newer equipment that we bought in the last 5-7 years. And that means different kinds of processes run through it for the same step. And so matching becomes a very, very important piece of the whole, keeping the processes under control. To get high CPKs, you have to match everything as best as possible. So we're using these AI ML techniques to automate some of these tasks. So we have been using this now at least since 2022, if not even earlier, to use this AI ML techniques to match the systems. Huge amount of improvement. And these are not insignificant. We have been able to improve. We're an automotive factory, right? The chips that we make probably are in the car that you drive today. Most likely, in fact. I mean, we make sensors, power chips, and other things, motor drivers, those kind of devices that are most likely in your car. The automotive industry is a very demanding industry. Everything has to be, of course, safe, but in order to make it safe, you have to make it uniform, the same. No matter what it is, it has to be the same every time. So CPKs need to be driven higher to be competitive. We have used this to do that. In the interest of time, I'm going to keep going a little bit faster. This is another thing. We have, I said, about 500 pieces of machinery, about 300 or so different flows, probably 20, 30,000 charts, SPC charts at any point of time. At one point of time, we had a quality issue, and as a manager, I told everybody in the company to own 10 charts and look at them every day. But that was not going to work for too long. That was just a frustration thing that I took out. But anyways, now we're using these techniques, AI, ML techniques, and these things look at 15, 20,000 charts. This 15,000, this is from a while ago. So probably a lot more charts are being looked at every day and constantly being tracked. We're saving a lot of wafers that we would have thrown away by using these techniques. This is more of a kind of a visual slide. I don't know if you can read the words from the back. But again, we're using these natural language processing techniques. This is something that we started using in the last 2 years or so as things have become more mature in this part of the world. We're using it for simple questions that engineers can ask, new engineers can ask, people who are being, especially the technicians who are on the factory floor and don't have bachelor's and master's and PhD degrees. They need to get quick information. They are now able to use these kind of techniques to get some of that information. So they get process questions answered, device physics type of questions answered. You don't need to be a physicist. You can get some of these answers pretty quickly. So we're using a lot more of these kind of techniques. As I said, the defect classification, defect map classification was one of the initial successes. This was, again, resource intensive. So we have a lot of fancy machines that we buy from companies like Onto, KLA. I don't know if these names are familiar to you or not. These are fast imaging. So they will take a wafer and take hundreds of images. I mean, they can go through 400 wafers in an hour, right? And they'll take 100 images each. So that's a lot of images that these machines are creating. In the past, of course, generally speaking, a human would have to see a sample of those images, and if you get lucky, you find a problem and report it and fix it. Because remember, the minute you got the image, it's already gone through a lithography operation, a etching operation, probably a deposition operation before it shows up to this imaging. So we've already kind of no way to recover any of this stuff. So the damage is already done, right? So you want to be able to catch things as fast as possible before the damage over about 10 steps accumulates to, let's say, 2,000 wafers. If you can restrict it to 25 wafers, that's a good thing. So we've used this. The accuracy has been fantastic. Of course, you can see here that it's about 100 times faster than using a human. That's not a surprise to you, of course. Now let's move to things that I see as opportunities and how we can get better at what we do. So we have a lot of different kinds of engineers in the fab. We have, of course, facilities engineers, there's civil engineers, mechanical engineers, chemical engineers, and then we have equipment engineers and equipment technicians, 2-year and 4-year graduates that work in a variety of different areas, different processes, photolithography, etch, measurement, front end of line, back end of line, so metallization, diffusion, implant, epitaxy, and so on and so forth. And then we also have integration engineers who put the full flows together, and device engineers and device design enablement engineers who talk to our customers. By the way, I should start with this. We are a foundry. We're like TSMC, but tiny, right? So that's what we are. So we also have design enablement as part of the offerings that we give. And then we have, so that's just the technology piece of it, right? That's just the technology piece of it. And I tried my best to capture AI ML, and that's the picture I could come up with, is that human head with some circuits inside it. So that's what it is. So that's my way of representing AI ML. And so you can see here the message. What I'm saying here is that at almost every one of these engineers' jobs, there's an optimization, there's a improvement opportunity. And the examples that I have shown you at this point are things that we have done, like, let's say, metrology or defect that we have done to some extent, right? We got some success there. One of the biggest issues, the other success is somewhat intelligence in scheduling the lots through the line. That's another little bit of success there. But the real issues still are process control. How do you get the equipment inputs, which is pressures, temperatures, flows, RF powers, and things like that, correlated to inline, which is thicknesses, uniformities, critical dimensions, and so on, correlated to the electrical sheet resistances, threshold voltages, breakdown voltages, and so on, to the product at the end, which is, the functionality, the probe, the product information that you get out of probing each product. That control is not easy to do. There's a lot of data. The quantity of data is immense, and it is, and I'll come to the next slide, which is where the challenges are. But before I move to the next slide, I also want to talk a little bit about the speed. The top level there is what makes a company successful in the semiconductor world. If you don't have technology, nobody's going to talk to you. If you don't have technology that you can bring to the customer and to the market quickly, they're going to give up on you and go to somebody else. And at the end of the day, if you can't manufacture it for the cost they're looking for, and somebody in Taiwan and China or Korea or, for that matter, Japan or even Europe can do it better, you're gone. They're not going to hang around with you for too long. So that drives the industry. In my opinion, the technology piece is the most important, because that's the getting inside the door piece. And that's where I think the biggest challenge and the opportunity for AI/ML is. I think we're doing a decent job in terms of speed and in terms of optimization. And that side is the operational technology, the IT people who work in the fab, the industrial engineers, automation engineers, supply chain people. You got to get all these things optimized. There's also a training piece of using AI/ML for training. We have done that. We've also looked at a lot of different ways of improving it. Huge opportunity for academic institutions to support companies like Polar. In the interest of time, I'll move to my second to last slide, challenges. This is the reason we are not where we would like to be, and where I think the kind of knowledge and information that's sitting in this room and the kind of knowledge and information we are using is at least 2 orders of magnitude different. We are using a very, very small part of what you all have here. And some of the reasons: data quality is poor. Cleanliness of data is messed up. There's all sorts of data sources. We have machines that are from the 1980s to 2020s, right? So they're all very different. Then we have vendors. All these small, I'm telling you, the number of people approaching me to sell their AI/ML products has surged in 2024. I did a survey yesterday before while I was getting myself ready for this talk. 1 to 2 in 2022, 2023. 50 almost in 2024 and 2025. So it's just all these companies are springing out. They all can solve all the problems that we have. But our problem is that, again, we are a small company. We cannot go and make a big investment in a small company that's going to fold, that's going to get bought out by somebody, and their whole agenda is going to change, their product line is going to change. So we need something different than these companies. And there's also not just the size of these suppliers. The other problem is the intellectual property. They are dealing with other people's data. Oftentimes, the companies that make the machines for us, the Applied Materials, the ASMLs, Lam Research, and KLA and others, they claim the data being generated in the fab as theirs. So there's also controversy there in terms of just the standards that need to be established across the ecosystem in the semiconductor business, that who really owns the data, who gets to manipulate it, who gets to use it, and so on and so forth. That's not an easy problem to solve. By the way, Applied Materials will sell the machine, but the software belongs to them. We're leasing the software. So there's some interesting dynamics there from an intellectual property point of view. And partners. We have tried to work with other companies in the ecosystem. Semiconductor industry, I don't know about other industries, but I feel like we're a little bit overly paranoid about data sharing. I think one of the famous books of the semiconductor industry is Only the Paranoid Survive. So that's maybe comes from there. Many of us do business with Department of Defense. So data sharing becomes another issue because the Department of Defense has ITAR trusted other kind of CMMC2 type of regulations. And then the other problem is, as I said before, the TSMCs can have 400 AI engineers. We have 2. There's just no way we can compete. And the gap is just going to get bigger unless we find a solution that closes that gap. And this is the way I think we can go ahead and really means what I'm trying to, the message I want to send here is that the only way companies that are small to medium, it doesn't have to, even companies that are medium sized, that are $2 billion companies revenue, or less than $10 billion companies, they don't have the same kind of ability to put a gigantic team together. So they're all in the same boat. There's a huge opportunity for a consortium that could be set up at the University of Minnesota or Purdue or one of the universities represented here. And we work very closely already with U of M and Purdue and some of the other colleges represented here. But that combined with a way that we can share data that can be anonymized or to some extent normalized would be a way to get this done for companies like Polar. So with that, I'll stop, and if you have any questions, we're happy to answer.
Surya, that was wonderful. Thank you so much. Please, Nikunj.
Yeah, thank you for that talk. Really nice there. Are there anything that you can share, like kind of unexpected insights that you got from your use of AI?
A good question. So the question is, did we have any unexpected insights out of AI? I think I have to say the unexpectedness was the amount of data that it could look at very quickly. The speed was unexpected. Personally, I knew that AI was going to speed up things. Analytics would be much faster. We don't have gigantic computers either, right? So we have, and I will be, I will expose my ignorance if I try to tell you what kind of computational capabilities we have at Polar. But I am sure we don't have the latest and greatest, big servers. So I was quite impressed that we were able to take all of this data and get something useful out of it in a very short time. And the other thing that I was kind of happy about was a lot of this information in the public domain that our engineer could use to get to some of these solutions faster. Not everything had to be invented at Polar. So a couple of things that I think were useful.
Thanks for the fantastic talk. Mike, I'm curious, like, from you identifying an opportunity for optimization to getting data and then getting out a model and then kind of quality control it, how long, and then deploy it finally, how long is that process going to take, generally speaking?
So that is, again, a very good question. And a lot of it is, so one of the things I personally think that we should be doing is most return on investment is target things that will give us useful results quickly that can either drive technology or speed, sometimes cost. So if we find a problem that we determine, or somebody we collaborate with, for example, in academia, jointly determine would be a good problem to solve using AI/ML, I think we can then put the amount of resources that we need. Right? If I know that I can solve a problem that can generate, $1 million in savings or $2 million in savings in 1 year, we can throw 5 engineers at them. Right? We can hire engineers. We can even get outside people. So the timeline, personally, we have done all of the things that I showed, and this is just a very small subset, has all been done since 2019. So that's 6 years with one person most of the time, right? Half person most of the time. So I think a lot of these solutions can be implemented or at least formulated and a solution found in less than a year and then implemented in about 18 months. I think that's the timeline that we look for.
Thanks for the wonderful talk, and I'm really impressed how much you did with one person in 6 years. Are they looking for PhD positions? Okay. My question was, you showed a hierarchy of opportunities, and you listed materials and effluents, and I'm a chemical engineer and a chemist, so I was curious to see what kind of opportunities were you thinking about there, and if you could elaborate on that.
I'm glad you asked that, because I think there's at least, I know there's one company here, right here at the University of Minnesota, that's working on using some of these techniques to develop new materials or understand existing materials. So part of the technology piece, right, the way we get differentiated from other companies in foreign countries is that we march on the path of new materials. And new materials is a significant opportunity for the semiconductor companies. For example, Polar is now one of the first companies that is going to make gallium nitride on silicon at an 8-inch platform. So we'll probably be the first. We're working with Renesas of Japan to get that done. So that's just one thing. Then there's going to be some kind of AlGaN or some kind of other GaN or some kind of other material that gets us to the, instead of going to 650 volts or 1200 volts, we need to go to 1700 volts. We need engineered substrates. All of these kind of opportunities are there. And I believe that some of these can be solved by the techniques that you are all working on. There's at least 2 companies I'm aware of, startups that I'm aware of, are already doing very interesting work in that world. The effluence and that piece goes to some of the environmental regulations that we have. For example, PFAS was one of a big concern that was raised. I think it's becoming a less of a, or at least it's being pushed out now, or we're getting more time now, whatever it is. But these are kind of things that I don't think the industry is super motivated to solve on its own. It's going to have to be pushed to solve these kind of problems, environmental problems. And if AI ML has a solution that we can make this thing faster, I think it'll be very, very useful.
So I wanted to applaud your bringing up the issue of data set size and one approach to at least addressing some part of the problem. I wanted to also ask about market power, which often is what forces contracts to go one way or the other, and about data that is not suitable to make open. Do you worry about having your proprietary data used and made available to your AI service providers? They would be doing this potentially from your competitors too. They may, for today, not do anything bad, but 5 years from now, they may know more about multiple industries, or at least some specific aspects, and then choose to exploit that market power, for example?
I mean, you hit that nail right on the head, right? This is exactly the issue, is that every company like Polar, right, if you go to, just in the Twin Cities, we have 5 or 6 semiconductor-related companies, Honeywell, Polar, Collins Aerospace, which is part of Raytheon, Skywater Technology, and Seagate, to some extent, affiliated semiconductor. Just between these companies, it is very difficult for us to kind of get that data and give it to an entity that is going to use that and maybe even help us, because a lot of that can be used for others. We are very sensitive to that problem. And that is why the data cannot be given in as-is form. It has to be changed to a different form, normalized in some way, or I don't know what the solution is, but it has to be changed in some form so they cannot revert back and understand that what we are doing, right? So some of these things are, especially the intellectual property in this industry is super important. A lot of it is not necessarily in patent form. A lot of it is in kind of homegrown knowledge type of form that goes into a lot. I mean, our process flow has been developed over 50 years. The power technologies that we have, not everything is patented. But if you give the data, there's a huge risk that that company can give it to somebody else and they can recreate what we're doing, right? That is something that we cannot accept. And so there has to be a way. And that's another thing that is a challenge for your community here, is that how do you help us mitigate that problem?
So are you able to say something about how you're addressing that problem today?
Right now we're doing everything internal. So that's, which I don't think is sustainable. So we have to find a way of doing it with other people. And the minute you go to some other company, all of these can of worms open up. And there is no standard, there's no, there's cybersecurity standards and other things being developed by SEMI and Semiconductor Industry Association, things like that. There's no data sharing standard. There's no rules for it either. Another opportunity for a consortium to maybe develop. For example, the Smart Institute, right? The Smart Manufacturing Institute would be a place where some of these things can be developed.
And on that count, I did lie. We'll just take Ganesh take a quick question, and then maybe we'll.
It related to the SMART consortium was the question I was going to ask you. What plans do you see for digital twins at Polar? And the second part is if Applied Materials controls your equipment and doesn't give you access to your data, how can you build digital twins and utilize them for your advantage?
Yeah, so I think, could you repeat the first part? I got the applied materials piece. What was the first part of the question?
Part is, what are your plans for digital twins?
Oh, yeah. So again, that's another. So we are looking at figuring out how to use digital twins. I think that has much higher potential than a lot of these things we're doing in terms of process control, because it's you can really understand what's going on a discrete level basis, like at one machine on one process, you can figure out what's going on. So that's something that we haven't done anything yet, but that's part of the roadmap. The data with Applied Materials and all of these other companies that are there is that the data is accessible to us. Right? We pull that data because it's coming to our MES system, the manufacturing execution system. All of that data is accessible to us. We can do whatever we want with it internally. What goes back to the question is that if we're going to go use a third-party vendor to do some, get some help, or share it with a different company and combine data sets. Again, I have an etcher. Every semiconductor fab in the world has similar etcher. The recipes are also not that different. They all have BCL3 and CLF4 and the same chemistries, similar powers. So there's an opportunity for an etch machine data to be shared from company A and company B and company C, pooled together and kind of come up with a common solution. That's an opportunity there. But Applied Materials will probably not like that. And Applied Materials will not like that because one fab etcher machine might be a Lam etcher, and we have an Applied Materials etcher. So that could be another problem too. So there's some serious kind of just logistics and legal problems that we have to solve.
Thank you very much, Surya.
Thank you.
We're running a few minutes late, so we're going to cut questions at this point. Thank you so much.